So this will be the end of section 1.3, on the section on continuity, and it's the algebra part of this. For each of the problems in the back half of this video, we're going to be given a function, and the instructions are going to say find where it's not continuous, find where it's discontinuous. Sometimes the graph will be continuous everywhere, or the function will be continuous everywhere if we took the time to graph it. And you don't need to state a reason, you don't need to sketch a graph, although for these examples I sketched a graph just so you could see visually what's going on. First problem is the function, first example is the function f of x equals 6 over x minus 1, and we're just supposed to find where it's discontinuous. Anytime I have a fraction, to find where it's discontinuous, all you do is ignore the numerator. If you do any algebra with the numerator, you're going to find the x-intercept, which has nothing to do with a break in the graph or a point of discontinuity. So anytime I'm asked to find the values where a graph is discontinuous or the function is discontinuous, if it's a fraction, I solve the denominator equal to 0. And that's going to give me where the graph is discontinuous. It's not going to give me the reason, but I'm not asking for the reason. So algebraically, for this example, to find the values of x where this fraction, the graph of this fraction will be discontinuous if we graphed it, you ignore the numerator, you set the denominator equal to 0, and this graph is not continuous, or equivalently, because I use these words interchangeably, it's discontinuous is the same as not continuous at x equal to 1. And I took the time to draw a graph. At x equals 1, this graph has an asymptote. So it would be a reason 1 if we're doing reasons, but we're not having to do reasons here. We're just doing the algebra part of this to find where the graph is discontinuous. And if the function is a fraction, you ignore the numerator, you set the denominator equal to 0, that gives you the value where it's discontinuous. Doesn't give you the reason, but we're not asking for the reason, so it doesn't matter. If I took the time to make a graph, then you could see that this is a reason 1 because it has an asymptote. Next example is another fraction. And same idea. I'm asked to find the value of x where a fraction is not continuous or where it's discontinuous. I absolutely need to ignore the numerator of x squared plus 6x minus 7. Has nothing to do with breaks in the graph. For any time I'm asked to find the values of x equal to a, or the values of x where a fraction is not continuous, I take the denominator, set it equal to 0, and do the algebra. This graph isn't continuous at x equals 1. This graph is discontinuous, if I want to use that word, at x equal to 1. I took a second to sketch the graph. This would also be a rule 1 because there's no closed circle point. This is interesting. This graph doesn't have a vertical asymptote. Usually if you set the denominator equal to 0, you get a vertical asymptote, but you can get a hole. So when you set a denominator equal to 0, graphically it's either a vertical asymptote or a hole. And for this particular fraction, because this fraction can be reduced, if you factor the numerator, you can cancel out the x minus 1s. If you're able to cancel the denominator with the numerator, instead of getting a vertical asymptote, you get a hole for what it's worth. But not important. We don't need to know the reason. This would still be reason 1 because the function's not defined there because there's a hole that's not plugged for what it's worth. But let me just focus on the algebra and stop doing the explanation, which is fun for me but pointless because I'm not asking it. Well, maybe I might back off that and still give you a little explanation here. So the function here, same instructions, find where the graph is not continuous. It gives me a piecewise function. Well, the only place a piecewise function can be discontinuous if each of its components are polynomials, which they are here, is at the value where the pieces are defined. So this function, it's either continuous everywhere or it's discontinuous at x equal to 6. To find the values if you're given a piecewise function where it's not continuous, we take the value that's given and plug it into the top piece for the x and the bottom piece for the x. When I plug 6, which is kind of the trigger number here, into the top function, I get 1. And on my graph, I mark that point 6, 1 with a solid circle. We're not doing graphing, but I did it, so I want to show you, because of the or equal to. When I plugged 6 into the bottom one, I got 3. And on the graph, that shows up as the point 6, 3 with an open circle. When I get these graphs that go in one point and out another, I have to define them as piecewise functions. So because these values are not equal, since the calculations aren't equal, or since these are different numbers, it's not continuous at 6. And you can see it graphically, but you don't have to graph. Since these are numbers, the function is not continuous at x equal to 6. This is discontinuous at x equal to 6. It would be reason 2. You don't need to know the reason. You just need to know where it's discontinuous. And if I give you a piecewise function, the only place it can be discontinuous is at the number that's in common for both of the pieces. And if we plug those numbers into the functions and get different results, it's not continuous there. It will actually produce a reason 2 going in one point and out another. The next function here is another piecewise function. To figure out so a piecewise function can only not be continuous if the pieces are polynomials, which they are here, at this common value. Well, let me do this here to see if it's discontinuous at this common value. I'll take the given number, plug it in for x in the top, plug it in for x in the bottom. I get 3 when I plug it into the top, 3 when I plug it into the bottom. It's continuous at x equal to 6 because they have the equal values. So this function is continuous everywhere. It could only possibly be discontinuous at 6, and it would only be discontinuous at 6 if these numbers are different. And here's the graph. This is the left half. The left half that is this, it would have a closed circle, and the right half would be this. It would have an open circle, but you can't tell the circle's open because it's closed up by the other one. So this would be the graph. It's continuous everywhere. So if you're given a piecewise function, it's either continuous, it's discontinuous at this value, or it's continuous everywhere. It's discontinuous at this value if you plug it into both and you get a different value. It's continuous everywhere if you plug it into both and you get the same value. This function that I'm asked to find where it's discontinuous, it's not a fraction, it's not a piecewise function, it's just a polynomial. And polynomials are continuous everywhere. The graph of this, it's not a fraction and it's not a piecewise function. And for our purposes, if I give you a function that's not a fraction, like the first couple examples, not a piecewise example, like the next couple examples, it's going to be continuous everywhere. There's not going to be any breaks in the graph. And again, I took the time to graph it. The graph looks like this. It's one smooth piece, no breaks in it. But algebraically, there is no algebra to do. So in this next grouping of problems, we're going to be given 3 kinds of problems that we're looking for points of discontinuity. Fractions, where we ignore the numerator and set the denominator equal to 0. Those values make the graph discontinuous. Piecewise functions, where we plug the number that's given into both functions. If it's not equal, that's where it's discontinuous. If it's equal, it's continuous everywhere. And polynomials are always continuous everywhere. So into the homework now. And all I'm going to do is find where the graph is discontinuous and not make any comment about the reasons. So same instructions that we've been doing. In problem 12, to find where the graph is discontinuous, I'm going to ignore the numerator of x plus 1. That actually graphically, if you set it equal to 0, doesn't give you a break in the graph. It gives you an x-intercept. I'm going to solve the denominator equal to 0. Add 5 to both sides, add 5 to both sides. And this is not continuous at x equal to 5. When I typed up an answer, I just wrote x equal 5. You could, that's enough. That answers the question. Find all the values of x where it's discontinuous at x equal to 5. You could be more verby. Not that that's a word, but I teach math. I guess I can live with that. This is discontinuous at x equal to 5. But it's sufficient just to write the value down. The way the question is worded, the discontinuous part is implied. So when I start writing my rest of my answers, I'm just going to write down the answer to the algebra and stop. Not giving any reasons for this part, and I'm not using these words if I want to be, efficient. Question 14, I'm going to ignore the numerator. Finding where a fraction is not continuous, or a fraction is discontinuous. The numerator has nothing to do with whether it's continuous or not. It has everything to do with the reason. You might get a different reason if we were listing reasons, but we're not. The algebra to find out where the graph of a fraction is discontinuous is just to take the denominator and set it equal to 0. I could say this is discontinuous at x equal to -1, but it's not necessary. I just have to give the value of x. Problem 16. I'm going to ignore the x squared minus 9. I'm going to solve the x plus 3 equal to 0, minusing 3 from both sides. This graph is not continuous at x equal to -3. Still going to be a reason 1. It's not defined there. Don't need to give reasons. Problem 18, still a fraction. If I'm asked to find the values of x where a fraction is not continuous or where it's discontinuous, I ignore the numerator. I solve the denominator equal to 0. Because there's a square here, I need to solve by factoring, and hopefully your factoring skills are good enough that you can do this easy factoring even though I'm not explaining how I did this factoring. This factors into x plus 1 and x minus 3. If you need help remembering factoring, you should come visit me and I can try to review for you. But this is a skill that comes up often in our class, so you should have basic factoring, easy factoring like this in your repertoire. So it's not continuous, or it's discontinuous at x equal to -1 and x equal to 3. Next problem's a polynomial. Polynomials, no algebra, they're continuous everywhere. It's not a fraction, it's not a piecewise function, it's going to be continuous everywhere. There's no algebra to confirm that. You can graph it, and the graph won't only have one piece, it won't be broken. 22, not a fraction, not a piecewise function, it's continuous everywhere. The graph is going to be a parabola that doesn't have any breaks in its graph. No algebra for that. Now the piecewise functions. In 24, it's either continuous everywhere or it's discontinuous at 2. For the piecewise functions, I take the value that's in common and plug it into both pieces. If I get the same value, it's continuous everywhere. Because I got different values, it's discontinuous at that value of x equal to 2. So this, if I was being verby, I can say it's discontinuous at x equal to 2, or just write x equal to 2 down. For 26, it's a piecewise function. It's either continuous everywhere or it's not continuous at the point that's mentioned in both of them. This one's a little bit tricky because you almost get a number that looks the same, but 1 and -1 aren't the same number, so this is discontinuous at x equal to 4. And you just have to write the number down the way the question was posed. The words are implied. I'm just answering the question without repeating the question in my answer, or any portion of the question in my answer. For 28, piecewise function. When I'm asked to find the points where a piecewise function is not continuous, I take the common number, plug it into both. If I get a different number, it's not continuous at that point. If I get the same number, it's continuous everywhere. So 28 is going to be continuous everywhere. Going through this fast, but this is pretty easy, and I don't think you probably have to watch every second of this. And this will be the last problem anyways. So for 30, it's a piecewise function. To find out where it's continuous or discontinuous, I take the common piece, the common number, plug it into both. If I get a different number, that's the value where it's discontinuous, because I got the same number, it's continuous everywhere. So that's everything for section 1.3. And what's coming up next is 1.4 and 1.5. I wrote 1.4 to help you understand 1.5. I'm not sure how much it does or doesn't help. If you jump right into section 1.5 and it doesn't humble you, 1.5 is on the test and 1.4 isn't. So you might, if you want to, just try to jump into 1.5. If it feels like a complete mess, then go back and watch 1.4. 1.4 isn't on the test. It's there to help you understand 1.5, and I'm not sure whether it really does or doesn't. So we'll stop the video and we'll just keep pushing through the chapter.